All right. Thank you very much, Sean, for that warm intro. Right. Pretty much Kaia, everyone. Super excited to be here once again for lesson one. Yesterday we kind of like did the kickoff session, which actually went well. And so officially we are starting the bootcamp, and this is lesson one, where we're going to be talking about blockchain fundamentals and also overview. So once again, welcome to the first lesson. And yeah, I pretty much know that you guys are going to learn quite a number of things about blockchain, the core components of blockchain, and also blockchain use cases, all wide range, right? So yeah, before we get started, a little bit of introduction about myself. Once again, for the sake of those who didn't join yesterday's kickoff call, my name is Peter Ayo, and I currently work as a DevRel engineer at Kaia DLT Foundation, right? And so the next on the agenda is to actually talk about today's class. What are we going to be looking at in today's class? So I think I already hinted, we'll be looking at blockchain overview, looking at blockchain core components, and also blockchain use cases, right? I think it just makes sense to talk about the blockchain fundamentals and also the overview, because quite a number of persons on this call are newbies, right? Who got to know about blockchain or Kaia when we posted about the bootcamp. And so this first session is basically meant to like water the ground and get you up to speed about what the concept of blockchain is, generally. All right. So I think we can move forward to the next one, which is blockchain overview. Right. And so we want to talk about blockchain. I know quite a number of us have been hearing blockchain, and whatnot. And probably you might be wondering, what even is a blockchain, right? So in simple terms, I think in today's call, I'm going to be explaining what a blockchain is from the lens of two things. First, how that it was coined from two words, which is block and chain, and then just give us like a simple overview of what blockchain is. Now, in simple terms, right, a blockchain is a shared and also distributed immutable ledger, which enables the recording of transaction and also tracking of assets within a particular network. This is so just to ensure that there's a single source of truth. And now, when we say that a blockchain is shared, it means that the copy of the blockchain data is available across various multiple computers. And now these multiple computers are called nodes, which are responsible for, validating and securing the blockchain network, right? And so when we also say that a blockchain is an immutable distributed ledger, we say that it has a copy of the multiple nodes or the multiple computers as a copy of the data of the blockchain on their computer, right? And it is distributed geographically in various regions, right? So take, for instance, a particular node can be located in, let's say, Latin America, or another node located in Singapore, or certain regions in Asia. And all of these nodes are interconnected together, right? Pretty much what a blockchain is, right? So what I've said is that a blockchain is first a shared and also an immutable distributed ledger, which enables the recording of transactions first and also tracking of assets within a network, right? Two things are important here: the recording of transactions and tracking of assets, and how that the copy of the blockchain data is distributed across multiple computers. And now this is what makes the blockchain decentralized and also immutable, right? Very quickly, we can also liken a blockchain as a distributed ledger. In this case, taking Google Sheets as an example, right? Quite a number of us use Google Sheet, right? In a case where you have a Google Sheet and you kind of like share your Google Sheet to quite a number of people who you want them to have access to the Google Sheet, they have the copy of the data on the Google Sheet in their computer, right? And the moment you make changes to your Google Sheet, every other person who kind of like has access to the Google Sheet also like have the copy of the new data. Now, this is what the blockchain is. Now, so this is blockchain from first principle, how that is both a shared and also an immutable distributed ledger, which enables the recording of transaction and also the tracking of assets within a particular network, right? Now, let's talk about blockchain from the lens of the two words, block and chain, right? Because these are like the two components that makes the blockchain. Now, you would want to agree with me first that before we go straight in, we have to understand what a block is, right? Now, a block is a fundamental unit of the blockchain, which contains various lists of transactions and also the cryptographic hash of the previous block, right? This, in simple terms, is what a block is. A block is first the fundamental unit of the blockchain that contains various lists of transactions and also the cryptographic hash of the previous block. Now, this is how a blockchain is linked to each other. Now, we mentioned that each block contains a cryptographic hash of the previous block, and also it contains various lists of transactions. In this case, what we are trying to say is that the way that the blockchain is kind of like linked to each other is by each block having a previous hash of the previous block. So now we are going to get into this scenario by taking a look at the next thing, which is block elements in this case, right? So what is like a block element? We've talked about block, and we've talked about how that various blocks are chained together with each other using like cryptographic hash, right? Which is the block hash. Now let's talk about block elements. Block elements, what do we mean by block elements? Block elements are those various things that makes up a block, right? There are those various components that makes up a block. Now, the first thing in your block, mind you, I kind of like mentioned that a block is what? The fundamental units of a blockchain, and it contains various transactions, and it also contains the cryptographic hash of the previous transaction. In this case, now let's take a look at what are the various components that makes up a block element, right? The first on the list is block size, right? Every block on the blockchain contains or have a particular block size. Now, what is a block size? A block size is the amount of transaction a block can hold, right? In most blockchain like Bitcoin, Ethereum, they have like an amount of transaction that their block can hold. And this kind of determines the network throughput and also speed. When we say throughput, is how like fast a blockchain can, propagate transaction and verify them on the blockchain, basically. So the first on the list of block elements is block size, right? Moving on, we also have block header. Now, the block header is basically a metadata of the block. Now, when we talk about metadata, we're talking about the various elements that needs to be included in like your block. Take, for instance, as you can see in the slide, we have the version number, right? We have the previous block, we have the timestamp, and we have the nouns, right? And also we have the Meku root, basically, in this case. Now let's break some of these things down, right? And explain them one after the other, right? So when we talk about like version, what do we mean by version? Depending on like the blockchain network, right? We have like a version number, right? That exists in your block. Now, I mentioned previously that a block is basically a fundamental unit of the blockchain, right? And also it has the cryptographic hash of the previous block. Now, the block header is that metadata that is being hashed to get the previous hash of the previous block. Now, in your block header, I mentioned that there are like 5 things that you need to consider. And depending on the blockchain and also the consensus mechanism that is being used, right, which we are going to look at in the next slides. Based on the consensus mechanism that is used, this determines what will be added in your block header. Take, for instance, in a proof of stake network, you're not going to add your nouns because it doesn't use mining procedures to validate transaction. Bitcoin actually uses miners, right? In the case where they have to compete for a cryptographic puzzle before transactions are being added to the blockchain. But in the case of a network using proof of stake, right, you need to add your validator signature over here. So these are like the elements of a block header, right? Moving forward, also in a block element, we have transaction counter. Transaction counter is the number of transactions stored in a block, right? Whether a block can hold up to 5 transactions or up to 4,000 transactions and whatnot. And then we also have transactions. Now, we mentioned that first thing is that the block is a fundamental unit of the blockchain, right? And also it contains a list of transactions, and also that it has the cryptographic hash of the previous block, right? So these are like the 4 elements of a block. First, it has a block size. It has a block header, which is basically the metadata of the block. It has a transaction counter. It also has the various transactions that have been validated and included in the block, right? Moving forward, right? Now let's talk about block hash, which is a very, very important element on the blockchain. So we've talked about the block elements, and from the last slide, we kind of like highlighted block header and how that in your block header, it contains some sort of metadata, and this metadata is what is hashed to get your block hash, right? So what is a block hash? I sort of like mentioned that, you know, the blockchain is first a shared and immutable distributed ledger, right? And also for each block, which is a list of various transactions and also is a fundamental unit of the blockchain, it contains the cryptographic hash of the previous block. Now, this is how we get the cryptographic hash of the previous block. For every block, the block header is being hashed, is passed into an hash function, and it returns an output, right? So what we are saying here is that for us to get the block hash, which is added into the block as the previous hash of the previous block, we are saying that you're going to pass in the version number, the previous block hash, the timestamp, the nouns, and the macro roots, right? In the case where it's a proof of stake network, you're going to be passing in the previous block hash, timestamp, validator signature, and also the macro root, right, into an hash function. And for the sake of those who don't know, an hash function is like a mathematical algorithm that takes in any large amount of inputs and returns a fixed amount of outputs, right? We're still going to look at this in like the slides where we're going to be talking about hash functions, right? And so what we are saying here is that for the most part, the block hash is how that security is sort of like maintained on the blockchain. So imagine hashing your block header, which kind of like gives it a pseudonymous value, right? It takes in your block header, then it passes it into the hash function, which is SHA-256. Just to mention also, the Bitcoin network uses SHA-256 as its hashing algorithm, while Ethereum uses KESHAC-256, right? Pretty much. Now that we have our block hash, right, this is how the blockchain is chained to each other. Let's take a look at how blockchain are chained to each other. Like I mentioned, a blockchain is made up of a series of blocks, right, that are linked together. So this link between the block is created using hashing algorithms, right? As you can see in this image right here, right? In this image, we have block 1, we have block 2, we also have block 3. Now, what we can see here is in block 1, we have the hash, right? We also have the previous hash. And for most blockchain, they have a genesis block, right? A genesis block is like the origin block. And most times it doesn't have quite a number of transactions, right? And this is where like the block originated from. And so if we have block 0, which is like the Genesis block, that is why on the block 1, we see that the previous hash is 000. Now in block 2, it has the hash of block 1. It has the previous hash of block 1, which is 6U9P2, as you can see. And in block 3, it has the previous hash of block 2, right? And so this is how the blockchain is sort of like chained together in this case. Pretty much how blockchains are chained together. Now, this speaks to the fact that one, how security is actually like enacted. Now, the first thing to note here is that before you can change any data on the blockchain, that means that you want to tamper with the block elements, with the block details, right? And so that will mean that you have to rehash the block header, which will provide a new hash, and it's sort of going to hinder the output in block 3. Now, let's take, for instance, in block 2, you have your hash and the previous hash, 6U9P2. In the case where we change the data in block 2, right, our hash is going to change here, right? And when we try to pass that into block 3, we expect that it should also change because the previous hash in block 2 already changed. And so imagine if you have up to like 1 million blocks in your blockchain and somebody tries to change a data in block 500,000, that means they will have to change all of the previous hash from block 500,000 to block 1 million. And most of the time, this takes a lot of like computational efforts for most, I mean, for the most part, for Bitcoin, for the Bitcoin network, it takes a lot of like computational efforts, right? Which of course brings us to the point that before you can successfully hack a blockchain, right, you need to be ready to change all of the block data for up to like 51% of the blockchain nodes available in a network, right? Which of course is impossible and of course is expensive to do, right? And so this is the concept of the blockchain. Just to reiterate, right, a blockchain in simple terms is first a shared and distributed immutable ledger that enables the recording of transactions and also the tracking of assets within a particular network, all for the sake of providing a single source of truth, right? That means that the blockchain in this case is just distributed, it is decentralized, it is secure, and also it's immutable, right? Because if you can't change any data on the blockchain, that makes it what? Immutable, right? We're still going to be talking about the pros and cons of the blockchain. But I hope that this definition and explanation of the blockchain kind of like sticks, right? Yeah, exactly. So it's tamper proof, right? Whatever thing you get to store on the blockchain remains on the blockchain because of the nature and the mechanism at which the blockchain has been built, right? Moving on, we're going to talk about so let's quickly take a look at the demo, right? Let's quickly take a look at the demo. I hope that everyone can see my screen, right? Yes. So all of what we have been talking about, how that the blockchain is a shared and immutable distributed ledger, and how that a block is a fundamental unit of the blockchain, and a block consists of various transactions and also the cryptographic hash of the previous block. Now, let's take a look at how this works in practice, right? And so this is like a website provided by Anders to kind of like show us how that these things work in real time. So what we are going to do is we're going to write any type of data over here. right? Like I mentioned, this is like an hashing algorithm, right? SHA-256. And for every hash function, you can pass in any large amount of inputs and it returns a fixed amount of outputs, right? So let's see this in practice, right? Let's take, for instance, you pass in block header, right? This is just a placeholder in any way. As you can see, it returns a fixed amount of outputs, right? Which is called a digest. Now, if you take in any type of data, probably you have a large chunk of text and you paste it here, you're still going to get the same length of hash. And so let me go to like lorem ipsum and then try to copy a text, like a long text, right? So regardless of like the length and the bulkiness of our inputs, as you can see, it returns a fixed length of outputs, right? So this is the concept of like an hashing algorithm. Like I mentioned, for the Bitcoin blockchain, it uses SHA-256, and for Ethereum, it uses Geshack-256, the same as Kaia, right? Pretty much, that explains the concept of hashing algorithm, because this is what is used on the blockchain for cryptography, for quite a number of the great things that we're going to be seeing in the next slides, right? Now, I talked about block hash, right? And a block hash is basically like the fingerprint of the block. When we say a digital fingerprint, meaning that it is like the unique identifier of a particular block. This is what a block hash means. In simple terms, a block hash is a unique identifier or a digital footprint of a particular block. And it takes in the block header. The block header contains your version number, your Merkle root, your nouns, and all of those details. Now, let's try to get a block hash, right? And what we'll do is, because we don't have one here, let's just input text and say block header, right? So we would assume that all of our block header metadata has been hashed over here, right? This is how block hash is being generated. Passing in all of the metadata in a particular block, and it returns the block hash. Now, going to the concept of blocks, we said that blocks are a fundamental unit of the blockchain, right? And it contains various lists of transactions, right? And also a cryptographic hash of the previous block in this case. Now we have block one, we have the nouns, which is part of like the block header, and we also have various data. Take, for instance, the various transactions that are here. Now, if you look at this, this field over here, it's currently green because we have an empty data, and the hash value over here begins with 4 leading zeros. Now, this blockchain demo is basically demoing how things work under the hood, especially for the legacy blockchain, which is called Bitcoin. Like I mentioned, Bitcoin uses proof of work algorithm, consensus mechanism, which means that miners have to, in a way, compete for a cryptographic puzzle, right? And what that means is that they need to find a particular value that helps return a hash function with 4 leading zeros. Now, if you can find a nouns that can provide a hash value of 4 leading zeros, I know that my transaction has been mined, or I'm successful as a miner, right? So in this case, what we can do is, if I try to input a particular data, as you can see, my transaction hash doesn't start with 4 leading zeros. So that means we have to find a nouns value that can return 4 leading zeros. And now this is where blockchain miners come in, right? Where they compete to find the cryptographic puzzle where a particular nonce value can give us a hash value that has or that begins with 4 leading zeros. So for us to get like a block that is successfully valid, right, we have to mine. And now when we wait for this to mine, we'd expect that the nonce to change and the hash values to change. And so for this data, this is the hash value that provides the 4 leading zeros that gives us a correct block hash in this case. I hope that makes sense. Yeah. So just to reiterate, this is also understanding the concept of block, right? And how that they exist on the blockchain for the most part, right? And so this demo uses like the algorithm of the Bitcoin network to kind of like explain to us how it works under the hood, right? So for most blockchain is also the same, where depending on the consensus algorithm, right? Once they agree on how the transactions should be validated, then once those agreements are made, the transactions are validated and added to the blockchain, right? In this case, let's say we have token transfer as the data, right? Now, we need to do something. What we need to do is we have to find the nonce that can provide the first 4 leading zeros in my hash. And to do that, we have to click on mine, right? So the nonce that provide the first 4 leading zeros in my hash is 14963. Now, so this is the concept of block and how block hash is being generated, especially on like the using the Bitcoin analysis. So we are taking a look at Bitcoin for a start because that's like the origin of like blockchain and blockchain systems, right? Moving on, let's take a look at how all of these things ties together, right? So we've talked about the blockchain, right? How that the blockchain is first a shared and also a distributed immutable ledger that has various blocks that are chained together, right? And so we want to say that this is block 1. As you can see, this is block 2. As you can see, this is block 3. This is block 4. And this is block 5, right? And also you can see that it has a previous hash of 00. Like I mentioned, every blockchain has its genesis block, which is more like block 0, but nothing actually going on in block 0, right? And that's why this is set to 0. Now, when we hash all of the block header, all of the block data, we get a particular block hash. Now, as you can see, this block hash is added into block 2 as a previous hash. 00015. We also have 00015, right? If you check block 3, it has the previous hash of block 2, which is 00012 and also 00012. And so this kind of like continues up to like block 5, right? Block 5 has the previous hash of block 4, 000AE, 000AE, right? So this is how blockchains are chained together and how the concept of blocks are chained together, which gives us the word blockchain in this case, right? I hope the explanation kind of like makes sense. Now, this will mean that if we try to mutate the state of the block, we are going to get an error, right? Because of course, we need to now mine for a nonce that will provide us the first 4 zeros in my new hash. Now let me place in NFT transfer right over here.
Hi, Ayo. Sorry for like disrupting you, but I think we have a question in chat. Someone asked have someone asked to explain what nonce is.
Oh, okay, awesome.
Just before we move on to the next one, just explain, I think, really quickly.
Yeah. So nonce is like a computational number that needs to be derived for your block to be hashed, right? So it is like that special number that miners needs to find, more like it's like a puzzle, right? That helps your block to be hardened. Now, once you get your nouns, it shows that you've done your computation under the hood as a miner. And then once your nouns is provided and your hash has the first 4 leading zeros, that means that your nouns is correct and that your validation can be added, or your transaction can be added to the blockchain in a case. If we go back to hash, right? As you can see, none of like all of the entry that I've been writing generates the first 4 zeros, right? If I keep typing on and on, none of these guys generates an hash with the 4 leading zeros. Now, so a nonce was introduced as a special number that can help us get to that figure that we are looking for, right? And what we are looking for is, for every sort of like block to be validated, it needs to generate a hash that has 4 leading zeros. And so for this part, that's sort of like impossible. You have to keep doing computation as to what number can I add to my hashing function that can provide 4 leading zeros. Now, this is what nouns are. Nouns are like special number that needs to be computed for by miners to be able to get the hash for a particular block. I hope that answers your question. Let me quickly check the chat. What is nouns? What is Meku tree? Okay, awesome. So nouns is basically being hashed onto. Exactly. Yes. What is Meku tree? Okay. So Meku tree is basically like a mechanism where like the transaction on the blockchain are being tied together. All of the transactions on the blockchain are being tied together, and it returns a value. Let me return this back to. So like it's written here, a Meku root is a value that is obtained after placing all of the transaction in a Meku tree. So Meku tree is also like a sort of tree that kind of like highlights how all transactions are linked to each other. And then it provides a single source of transaction hash that sort of like links back to every other transaction attached in a block. So this is what like Meku roots and Meku tree does, especially in the concept of like blockchain, is a way to sort of like compile all the transactions that exist in a block together, and how that you can easily retrieve back all the transactions that exist in a blockchain, in a sense. Let me exit this guy and go back to blockchain demo. Yep. So we're talking about blockchain, right? So now we've talked about block 1, block 2, and now that we have various hash or previous hash added to the different blocks, and we've seen how that in the case where we try to mutate a state, right, it provides a separate hash value. But then what we are looking for is for it to provide a hash value with 4 leading zeros. So that means that we have to mine. And when we mine, it kind of like provides us, it runs through like this mathematical algorithm to kind of search for the nonce value that is going to provide for a hash value with 4 leading zeros, given all of these parameters, right? And so when we mine, we see that this transaction has been validated here, but in other blocks, it is not being validated because, of course, it doesn't have the correct value. Now, the previous hash has changed over here. And so what we need to do is also to now mine the transaction again, so we can get a nonce value that provides the 4 leading zeros in this hash. So we are going to do this for block 3, block 4, block 5. And it kind of like open up like the question of we can mutate states or blockchain data on the blockchain. If we do that, that would mean that we have to keep changing the states of all of the blocks that are attached to that transaction, because they are all linked together, right? As you can see, this guy has the previous hash of block 2, and block 4 has the previous hash of block 3. And so if we get to change any data in block 2, that will mean that you have to also change data in block 3, in block 4, in block 5. And imagine if you have like a blockchain with a block number of like, let's say 150 million. And for some reasons, a validator kind of like propagated a wrong transaction. That would mean that you have to keep changing all of the data until it gets to the latest block, right? And so this is why the blockchain is secure and also sort of like immutable, right? I hope that kind of like does justice to what blockchain is in this sense, right? Do we have any questions? Before we sort of like move on to the next part. Yeah, right. Merkle trees is a data structure used in the blockchain to store hashes of data, right? It sort of like checks how all of the transaction in your data are being stored and also linked together, such that it provides a single source of truth for your transaction when called upon. Yeah, I mentioned proof of work. Yes, so proof of work is sort of a consensus algorithm, right? That the Bitcoin network uses, right? As we all know, Bitcoin is like the legacy blockchain, right? In this case, where all of the transactions on the blockchain, on the Bitcoin network, are being validated by miners, right? So when we say proof of work, it means that the miners have to compete for a cryptographic puzzle so that they can provide a hash value that is less than a particular difficult target, which in this case is like providing a value that has 4 leading zeros at the back of the hash, right? As we can see in the explanation or in the demo, right? So that's what proof of work basically is. And it's sort of like, what's it called now? Energy consuming, right? Sort of energy consuming, and it requires a lot of like computation and whatnot, right? So this is like the concept of proof of work. So is it possible that two miners solve the required hash at the same time? If yes, how will the system decide which will be the next block? So if it's possible for like two miners to solve the required hash at the same time, I think it depends on like the computational power of each of the miners, right? And how that you can quickly like go through what sort of nouns can be produced for this type of like transaction hash. So the way it works is that all of the miners sort of like have the copy of the blockchain data on their node. And once a transaction is kind of like propagated, the nodes pick that up, or the miners pick that up and sort of wants to run the mechanism, or wants to find the cryptographic value or the nouns that can provide a particular required hash at that same time. So if it's possible, I think it depends on like the computational power and how that the miners sort of like pick up the transaction when it's being propagated. And so if yes, how is the system going to decide which will be the next block? Not sure I got that, because for each time a miner gets to like find the nonce value and the block or the transaction is added to a block and the block is validated. Of course, whatever the next transaction in the mining pool, is going to be added to the list of transactions to be added to the blockchain. And because there's always like a mempool where transactions are, right? And so depending on how the miners can pick up transactions from the mempool, and this is how like they are sort of being bashed. And so for some reasons, depending on how much of gas that you can pay, right, the miners sort of like take a look at how much gas you are willing to pay for a particular transaction and sort of like do some priority. So for transaction that has less gas fees, right, they sort of like tend to keep that backwards in the mempool, and transaction that has higher gas fees are added sort of, or are being validated. Yes. So yes, it's always a single nonce because it has different data. I mean, for some reasons, you can't have the same data going on or being propagated into the block, right? In this case, take for instance, I might have a block number of 1. Of course, in the next block, it's going to be 2. So there are like various parameters that makes it to be different and for you to get a different nonce for each time. You said Bitcoin uses proof of work, meaning other blockchain doesn't. Yes, for the most part, I think it's only Bitcoin that uses proof of work as of now, right? Other blockchains have their own consensus mechanism. Take, for instance, Ethereum 1.0 uses proof of work, but Ethereum 2.0 uses proof of stake, right? Kaia uses IBFT, right? And also proof of stake, right? Awesome. I think that answers all of the question for the most part. I hope that we've now gotten like the concept of, the blockchain, how that first is a shared and also a distributed ledger for recording transactions and also tracking assets, right? And also a block is a fundamental unit of the blockchain. It contains a list of various transactions, and also it has the cryptographic hash of the previous block. Now, one of the things to note about a block is that every block has its block hash, and this block hash is a digital fingerprint of your block. Your block hash is derived by passing in your block header, which is the metadata of your block, into a hash function. And for the most part, might be SHA-256 or KSHA-256, right? And it returns a fixed length value, which becomes your block hash, right? And this is how like blockchains are chained together. A particular block has the previous hash of the previous block, and the next block also has the previous hash of the previous block, and so on and so forth. Right now, let's talk about blockchain core components. And now we have been talking about blockchain being like a shared and distributed ledger. What are those things that makes the blockchain what it is, right? And I think the first on the list is cryptography. I was talking about block hash. I was talking about hashing algorithm and whatnot. Now, this is where cryptography comes in, right? So you'd ask the question, what is cryptography, right? In simple terms, right, cryptography is the science of securing information with complex mathematical algorithms, right? For the most part, this is used for encryption and also decryption purposes. Decryption in the sense that it is only available or can only be accessed by intended parties. This is the concept of cryptography. I wrote here that it's the art of creating and keeping secrets. And in today's world, it is done using complex mathematical algorithms. Basically just encrypting data and also decrypting them, and such that, I mean decrypting in the sense that only intended parties can have access to the decrypted data. We are still going to get to that in a while, right? But I mean, in simple terms, this is cryptography. Is like the science of securing information using complex mathematical algorithms. And I already talked about various types of like hashing algorithms, right? I mentioned SHA-256, which is obviously used on the Bitcoin network, and also KSHA-256 used on Ethereum, and also Kaia. right? Now, bringing it back to the concept of blockchain, what is the primary use of cryptography in blockchain? Now, we're looking at three major use of cryptography in blockchain. The first is asymmetric encryption, which is basically public key cryptography, or which is used for generating key pairs. And we also have digital signatures and hashing functions, right? Now, let's take a look at them one after the other. The first on the list is asymmetric encryption, which is also public key cryptography. Now, how does this, or how is this important in the blockchain world? Now, in the blockchain world, we have the concept of key pairs, where we have a public key and also a private key, right? A public key is how that your Kaia address is being generated. And this is shared openly, right? Anybody have access to your public key, right? And also your private key is a value meant to be known by just yourself, right? You can use this as a scenario. Take, for instance, your email address. You can share your email address with anybody from anywhere around the world, but your password to your email address is meant to be known just to you. Now, this is like the concept of public key and private key, because with the password to your email address, now you can open your email and read whatever messages that you might have. Now, same thing applies in the concept of public key cryptography, is how the key pairs are generated on the blockchain, where we have a public key, which is used for your address generation, and also your private key, which is used for signing data and basically just initiating transactions on the blockchain. I wrote here that data encrypted with one key can only be decrypted by the other, right? So if you sort of like encrypt your message with like your address, signing the transaction under the hood with your private key, only your private key can sort of like decrypt that transaction, right? Well, we are still going to be talking about how this is useful. Now, number one way of how this is useful is address generation. All of the address that you see being generated on the blockchain, on Kaia, they go through something called public key cryptography, right? And this is generated from your public key. That's one part. Also, we have digital signatures. Now, this takes me to the next point of how cryptography is being used. Now, I've talked about public key cryptography, which is basically just generating key pairs, public key and private key. And I mentioned that your public key can be shared openly, and of course, it's used for like generating your Kaia address or your Ethereum address, right? And also, a private key is meant to be kept secret, only to be known by you, right? Pretty much it. It brings me to the next use of cryptography on the blockchain, which is digital signatures. Now, digital signature is a scenario where you get to append your signature in every transaction. Now, how do I mean? For every state change on the blockchain, or for every mutation on the blockchain, it is initiated by a transaction. And how does the blockchain knows that, oh, this transaction is coming from a particular account? Is through digital signatures, because under the hood, it uses your private key to sign the transaction. Now, think of it as this. You have a document, and take, for instance, a document from your bank talking about transferring your assets to somebody else overseas, and you need to sign. What you're telling the bank is that I approve of you to help me send transactions on my behalf. Now, this is like a digital footprint or a digital fingerprint of you telling the bank to be able to send transactions on your behalf. Now, same things apply on the blockchain. For every transaction that is signed by a private key under the hood, you are generating a digital signature. And this is useful because it sort of like provides integrity and verification. Now, blockchain nodes will be able to know that, oh, this transaction is coming from so address, and you can invalidate that you've signed a particular transaction. And whatsoever transaction that you signed cannot be tampered with because you actually used your private key to sign them in this case. And the second important use is non-repudiation, which says that when a party signs a transaction and submits it, you can't claim later on that you did not submit that transaction because your signature can be verified on the blockchain, right? So this is like the second use of cryptography. The first part, we talked about public key cryptography, which is basically generating key pairs. The second, we talked about digital signature, which is generating a digital fingerprint on every transaction, which basically is used for integrity, verification, and non-repudiation, right? I hope that kind of like makes sense. The next one is hash function. Now, after I quite like talked about block hash on the call and how that, you have to pass in a particular metadata into an hash function and it returns a fixed size value of output, right? And we kind of like saw that when I was demoing when I was demoing on the site that I showed a few minutes ago, how that you write any length of input and it returns a fixed length of output. Now, this is the function of hash functions on the blockchain. And they basically help you to like conceal or encrypt data in this case and returns a digest. A digest in this case is like the fixed length output, right? And so what are hash functions? Hash functions are mathematical functions or algorithm that takes a variable number of character or input and converts it to a string with a fixed number of outputs or output length. As you can see on the image on the right-hand side, we have an input fox, and we have cryptographic hash function, and then it returns a digest, right, which is like a fixed value. As you can see, this is a fixed value. The same value here is the same value size here and over here. And depending on the length of the output, it doesn't tell on the length of, or depending on the length of the length of the input doesn't determine the length of the output. As a matter of fact, the length of the output is always fixed, right? No matter the size of the input. Now, what are the characteristics of an hash function? First, it is deterministic, right? When we say an hash function is deterministic, we mean that you know that for every input is meant to give a fixed output, right? This is the concept of deterministic, that for every large input is returning a fixed size output, right? It's also fast. It does like the hashing process within seconds, right? As you can see from the demo. Also, it is one way, meaning that it is not possible to return from the original hash, which of course is the digest, back to the input, right? Back to the input. So it's not possible to go from the output back to the input. Now, this is the concept of one way. For also, one of the characteristics of hash function is that it has something called avalanche effect, where a small change in the input tends to generate a completely different output, which is the hash. As you can see from this guy, right, while we were trying to interact with it. So if I write OX pam pam here, it returns a fixed length of outputs, right? If I change this to OX pampa without the M, it returns a separate value of hash. If I take it back to OX pam pam, it returns the same value as before. Now, this is what we call the concept of avalanche effect, where a small change in the inputs, right, significantly affects the change in the output, right? As you can see, this is OX pampa. It returns ED, CB. And when I had M, it returns 4E, 8C, right? This is the concept of avalanche effect, right? And so I think I've been able to like do justice to the how that cryptography is being used on the blockchain. First, we talked about public key cryptography, which kind of like handles address generation and also digital signature. I also kind of like stressed a bit on digital signature and why it's important. It's important for the sake of integrity, verification, and also non-repudiation. Then we talked about hash function because quite a number of things have been hashed on the blockchain. Take, for instance, your block metadata, right? Your block header in this case, and we get the block hash, right? I think I've mentioned this already, that there are several secure hash algorithms that exist. We have SHA-256, we have SHA-3, and also KSHA-256, right? And so these are like the various algorithm or hash algorithm that exist. Moving on to the next blockchain core components, which is consensus. I think we already kind of like touched a bit on this in the past, or like in the last slides, where we were talking about proof of work, proof of stake, and whatnot. Now let's dive deep into what consensus is. So in simple terms, consensus algorithm, or consensus as an English term, is basically two parties reaching an agreement, right? That's the word in the literal English term. Two parties reaching an agreement, right? Now, when it comes to the concept of the blockchain, right, it speaks to the fact that the various blockchain nodes needs to come to an agreement on how to validate transaction and add them to the blockchain, right? So before we go into like the nitty-gritty, let's talk about something called the Byzantine generals problem. So this is an analogy used to describe the consensus mechanism or like algorithm, and how that blockchain nodes needs to reach an agreement, right? So yeah, the Byzantine generals problem is basically an analogy, right? That speaks to the fact that, oh, there is an army of generals, right? So I want you guys to pay attention to this. There is an army of generals who wants to attack a particular city at the same time. Now, but they have the problem of, oh, there might be faulty or malicious generals who actually don't want them to attack the city at that time. Or there might be interception in communication, right? These two things are very, very possible. Now, there is an army of general who wants to attack a city at the same time, right? But there are two factors that might be open to them not achieving that goal. First is that there might be malicious generals who have partnered with the enemy city or country, or there might be interception in communication, right? Probably when the honest generals are trying to communicate with other honest generals, there might be interception, which might hinder them from attacking at the same time, right? So here comes the challenge of, how does the honest generals who wants to actually attack the city at the same time actually attack the city even in the presence of malicious generals, right? Even in the presence of malicious generals, how does the honest generals actually attack the city? Now, this is the concept of the Byzantine generals problem, and it speaks to the fact that the same is also available on the blockchain, right? Where in this case, the blockchain, the army generals represents various blockchain nodes, right? Which needs to come to an agreement on how transactions are being validated on the blockchain. And then they need to come to a consensus in this case, where even if there is a faulty node or there is a malicious node, they still have to come to a consensus on adding transactions to the blockchain, right? So this is the concept or the analogy for Byzantine generals problem. And the concept of them proceeding even in the presence of malicious node is called Byzantine fault tolerance, right? Because they are building a system to be tolerant to the presence of malicious nodes. I hope that makes sense. Moving on, we have, okay, so what is the word consensus? I think by now you should have gotten a hang of what consensus algorithm is. So consensus algorithm is a mechanism at which blockchain nodes reach a consensus, or how transactions are being validated, and how that a single and valid copy of the blockchain is maintained by all the nodes in the network, right? Let me take that again. Consensus mechanism is an algorithm that is used by blockchain nodes to reach an agreement on how transactions are validated, and how that a single and valid copy of the blockchain is maintained by every participant in the network. Participants in this case means the blockchain nodes, right? Moving on also, this is achieved through mathematics, and it sort of like guarantees trust between the parties on the blockchain, right? So the next question is, what are the various algorithms that we have seen to work in the past to ensure that blockchain system or blockchain nodes sort of like reach consensus? And the popular ones that we have seen to work is proof of work, right? Which I already talked about. So proof of work is a consensus algorithm used on the Bitcoin network, right? As I've said before, it relies on energy for solving a sort of like cryptographic puzzle, right? In this case, what we are trying to look for is a nonce that can provide a hash with first four leading zeros in this case. So the nonce is more like a special number that needs to be solved, and that's like the cryptographic puzzle, right? The miners needs to find a way for them to sort of like, guys, to sort of like find a nonce. Okay. Find a nonce that can provide the first four leading zeros in the hash. So once this is done, they're sort of like incentivized, right? That's for proof of work, right? So in simple terms, it's a consensus algorithm that relies on miners solving for a cryptographic puzzle before transactions are validated on the blockchain, right? And it's mostly used on Bitcoin now, and it was used on Ethereum 1.0. Now, to the next one, which is proof of stake. In simple terms, proof of stake is basically a consensus algorithm where validators are selected randomly based on the amount of value that has been staked in the network. And also, a requirement is that the validator set needs to stake an amount before they are randomly being selected to propose or to be a validator on the blockchain. And now, so what that means is that if a particular node propagates a malicious transaction, a malicious block, you are being slashed from the amount you have staked, which is sort of like a method to like keep the blockchain running and secure. So this is called a slashing mechanism. And also, for the most part, when a proposer sort of like propose the right blocks, they are sort of like incentivized, right? So that's pretty much the concept of proof of stake, right? We have proof of work, we have proof of stake. We have quite a number of other consensus algorithms, but I'm going to be talking about PBFT, which is practical Byzantine fault tolerance. Now, I already mentioned the fact that, or I already stated the analogy of the Byzantine generals problem, right? Which is basically, a particular general army needs to attack a city at a particular time, but then there might be issues around, there are malicious generals, or there might be interception when we are trying to communicate with other honest generals to attack at the same time. And this brings us to the question or challenge of how does honest nodes actually attack at the same time, which can be brought to the concept of blockchain. In this case, the generals are the nodes, right? And so for the concept of PBFT, it basically talks about how that a blockchain network can reach a consensus in as much as the malicious nodes on the blockchain are not greater than or equal to 1/3 of the total nodes on the blockchain. So this means that for a transaction to be validated, right, 2/3 of the blockchain nodes, in as much as 2/3 of the blockchain nodes sort of like propagates the right transaction, or kind of like validates that the transaction is true, then they can add such transaction to the block, which is then added to the blockchain. So that is the concept of PBFT. And Kaia uses IBFT, right, which is like an optimized version of PBFT, which is responsible for like the 4,000 transactions per second and also immediate finality, right? Pretty much that's like the concept of the various consensus algorithm. There are quite a number of other consensus algorithm, but for this bootcamp, I think we'll just be talking about proof of work, proof of stake, and also PBFT, right? Moving on, we are being a shared and distributed ledger, right? So still talking on blockchain core components, I think we've talked about cryptography, we've talked about consensus. The next on the list is talking about the blockchain being a distributed, ledger or like a network, right? So when we say that a blockchain is a distributed network or ledger, it means that every copy of the blockchain data is available on all of the blockchain nodes available on the blockchain network, right? What does this mean? I mentioned that the blockchain network has quite a number of like multiple computers, right? Which basically are the one responsible for validating and securing the blockchain. Now, what a distributed network is a system where all of these multiple nodes or all of these multiple computers have a copy of the blockchain data on their nodes, right? And now, when we say a system is distributed, it's more of talking about how resources are shared and also how data are being shared in like a geographical and logical manner in this case. You agree with me that various nodes are stored or like are housed in various parts of the world. Like I mentioned, a node might be in like Latin America, or might be in like Asia, in various countries in Asia or various countries in Africa, right? But all of these nodes sort of like talk to each other, propagate network to each other, or propagate transactions to each other, ensuring that the blockchain network is secure, right? So this image also that I'll be sharing next sort of like explains the difference between distributed, centralized, and like decentralized, right? So like I mentioned, when we say a system is distributed, it speaks to the fact that resources or like data are shared between like multiple computers, right? In any case, if one of the nodes goes down, every of the other nodes available sort of like pick up the blockchain, and the blockchain is still running effectively, right? As you can see, as illustrated in this image, we have the circle teamed in yellow, how that they are connected to each other. And all of these nodes have, a copy of the blockchain data on them. Now, when we say something is centralized, it means that it talks more about authority, right? How that there is single control in a particular body or a particular entity. Now, as you can see in the image next to the distributed, all of the control, all of the authority is saddled to one party, right? Which is the guy in yellow, right? In this case, it has a limitation of central point of failure, where if this node goes down, then the network can no longer be active, right? We've seen this in the scenarios for like big tech companies like Facebook and whatnot, right? The next on the list is like decentralized, right? Where it talks more about authority, right? How that authority is not, or control is not in the hands of like a single party. It is distributed, or like it is shared amongst multiple parties, right? And that's why on the blockchain, there are no like central intermediaries or government bodies or whatnot, right? It is controlled by independent multiple parties or nodes that are available across various regions, right? And so this brings us to the concept of how that a blockchain can both be distributed and decentralized, right? In the case where distributed focuses more on how that resources are shared and data are shared across multiple blockchain nodes. And also decentralized talks about how that there is no central source of authority with a single control. Authority is shared across, various multiple parties. This is like the concept of distributed network, right? So now, having mentioned that, it just makes sense to also like talk about the pros and cons of the blockchain. We've talked about how the blockchain is a shared and also a distributed ledger that sort of like enables recording of transaction and also like tracking of assets within a network to provide like a single source of truth. Now, one of like the pros, which was, of course, is also advantage of the blockchain is security. The blockchain is secure, right? I think we already sort of like gave a hint into how the blockchain is secure. The blockchain is secure because it sort of like uses cryptography, consensus algorithm to sort of like ensure that blockchains or blockchain transactions are validated in the right manner, and how that each of these blocks have a cryptographic hash of the previous block. And as such, blockchain data cannot be mutated. You can't change the states of the blockchain data, which sort of like provides security. Now, in any case where a blockchain wants to be hacked, that would mean that they have to change the data in every block, for 51% of all of the blockchain nodes available in the network, which of course is sort of like expensive to do, right? If you ask anybody. So that's like the concept of how the blockchain is secure, right? The next on the list is transparency. When we say transparency, it means that every action, every step is publicly available to everyone, to anyone, meaning that you can track both inflows and outflows, how that an account sends a transaction from this point to the next point, which sort of like hinders money laundering and also like corruption sort of, right? Because you can track asset movements or asset flow, or how that data is being passed on from party A to party B, right? What we are saying here is that all the information or all the data that has been stored on the blockchain is publicly accessible, can be viewed by everyone. We also have decentralization. Decentralization in this case means that there is no single source of authority, which sort of doesn't bring in the single point of failure, right? The blockchain network is decentralized, how that it is not controlled by a single party, right? It is not controlled by a single party. It has multiple independent nodes, seeing to the affairs of the blockchain, and how that this ensures it's secure, and also transactions and decisions are being made independently by these nodes, right? The next on the list is accessibility. Now, this is like one of like the very cool one, where anyone with internet connection basically can just do stuff on the blockchain, can send crypto from party A to party B, or can basically just receive crypto from anyone from any part of the world, right? When we say accessibility, meaning that, I mean, even to like third world countries where they sort of like have issues with cross-border payments, with just internet connections, you can have access to programmable money, where you don't have to go to the bank before you sort of send money to somebody in Singapore or Korea. By just sending, stable coins, you are able to tap into like the financial world, especially the one provided by the blockchain, right? We also have like immutability. Now, this speaks to the fact that when a transaction or a data is being stored on the blockchain, it cannot be reversed, right? Or it cannot be rolled back. And while this is good, it's also sort of like a thing to optimize for. right? So if you are trying to build a feature where, you have to mutate things and whatnot, I think you have to consider whether you should use the blockchain or not. And if you are trying to build like a use case where probably you don't need to change any state, right? Or mutate whatever. Take for instance, if you are trying to build a decentralized voting system on chain where all of the persons that vote, their votes sort of like count, right? And so if a voter sort of like votes on chain, this data is recorded and nobody, not even the government, can either manipulate or sort of like rig the election results, right? So these are like sort of the pros of the blockchain, right? Now let's talk about the cons, which is the disadvantages that we've seen over time. The first is scalability. So what does scalability mean in this case? It means that blockchains most times struggle to handle mass volume of transaction, right? We can see this in the case of Bitcoin and also in the case of like Ethereum, where it can only handle 20 transactions per second at most, right? And that's why we have quite a number of like solutions to sort of like solve the scalability issue. And so it means that the scalability issue is something that we don't get to see, especially in like the traditional world, right? How that Visa can handle up to like 24,000 transactions per second, right? And that's why we have blockchains like Kaia to sort of like provide solution for enterprise grade services, right? That can handle this mass transaction or mass volume, right? So in the case where we have mass volume of transaction, there's usually like network congestion, which usually results to like high gas fees or high gas costs at the end of the day, right? So this is where Kaia blockchain comes in, because Kaia provides you access to be able to handle 4,000 transactions per second with like 1 second's block finality, right? The next on the list is speed. This still speaks to the fact that blockchain networks, or this reflects from like the limitation of scalability issues, how that it can process quite a number of like transactions at a go, and it sort of like limits how transactions are added. Take for instance, you're trying to build a use case around gaming, right? You want to ensure that it's fast. For the most time where a user is trying to play a Web3 game and initializes a transaction, imagine them trying to sign a transaction and it takes up to like 15 minutes. That's not really cool for the feature that you want to see added on the blockchain. And because we say the blockchain is secure and all of that, but then it doesn't have quite a number of speed, right? So this is where like Kaia also comes in to like solve this problem of speed, because of course it can handle up to 4,000 transactions per second and has 1 second's block finality or immediate block finality, right? What this means is that when you're playing your game, when you initialize your transaction, it takes like 1 second, even within like a blink of an eye, your transaction is being validated and added to the blockchain, right? We also have complexity, right? One of the things about blockchain is that it has a lot of deep learning curve, right? How that it's not beginner friendly to normies or to first timers. You have to understand certain technical terms. You have to understand wallets. You have to understand private key management. You have to understand how to do all of these things by yourself. And in case where you don't get a lot of guidance, right, you might lose your private key. And in the case where you have quite a number of money in your account or in your wallet might be drained, right? And for somebody experiencing this in Web3 might sort of like limit their experience or their exposure. And it's sort of like a blocker and also like a limitation. So we've seen quite a number of persons, talk about UX problem and also complexity problem, how that it takes up to like to onboard a newbie, it takes time to like onboard a newbie because you have to do a lot of like explaining some technical terms, off-ramping and on-ramping, all of those things. They get to know about all of those things. And for some people, it's sort of like complex, right? The next on the list is regulatory uncertainty, right? For the most part, blockchain laws or laws regarding the adoption of blockchain in certain countries are still like evolving, right? And so governments, on the other hand, are banning or restricting or setting like limitations on what can be done on the blockchain and whatnot. So this is sort of like a pain in the ass, sort of. And so, but I think that in the nearest future, we're still going to like see quite a number of adoption go for like blockchain in most countries and in most regions. So yeah, we've been able to talk about the pros and cons of the blockchain, how that the blockchain is secure, transparent, decentralized, accessible, and immutable. And for the cons part, which is like disadvantage, we talked about scalability, speed, complexity, and also regulatory uncertainty, right? The next on the list is the types of blockchain. What are the various types of blockchain? We have permissionless blockchain and permissioned blockchain. So when we say something is permissionless, it means that anyone can access it. Anyone from any part of the world can access it, right? Anyone can read, anyone can write and validate transaction without prior approvals, right? That means that you can just open up your wallet and write transaction to the blockchain. It makes it permissionless. The next thing that makes a blockchain permissionless is that it is not controlled by a single entity. It speaks to the fact that it is decentralized, right? And authority is not centered into one single person's hand, which is sort of like decentralized, right? Also, users don't need to reveal their identities. Like I mentioned, it uses cryptography to sort of like generate addresses, which is pseudonymous, right? In this case, hexadecimals. It uses public key cryptography, your public key, and also your private key to generate identities for you or like accounts for you on the blockchain, which you use to like interact also with the blockchain. And so for permissionless network, you can build various use cases around cryptocurrencies, DeFi, NFTs. When we say DeFi, we mean decentralized finance. When we mean NFTs, we mean non-fungible tokens, and basically just build quite a number of like decentralized applications, right? That's that about permissionless blockchain. And so examples of like permissionless blockchain will be Kaia, Bitcoin, Ethereum, and so on and so forth. But for permission blockchain, right, this is like the opposite of permissionless blockchain. Of course, it has governing entities. Only authorized parties are allowed to validate transaction. So basically, the opposite. All of the good stuff that I said about permissionless blockchain is the opposite of permission blockchain, right? It is best for enterprise solution, supply chain management, banking, and healthcare, because of course it can only be or used or accessed by authorized parties or intended parties. So this sort of like fits into enterprise solutions, supply chain, and also like banking and healthcare. Right, so very quickly, let's just rush through the other slides. So the fourth thing about the core components of the blockchain is smart contracts, right? You must have been wondering, right? In this bootcamp, we'll also be talking about solidity, right? We'll be talking about building smart contract and whatnot, right? And so smart contract is that piece that sort of like helps us build business logic on chain. Now we've talked about how that permissionless blockchain helps us to like build various use cases around DeFi, NFTs, and whatnot. Now, how do we bring business logics or like this sort of logics on chain? Is by using smart contracts, right? This is how business logics are being brought on chain. So smart contracts, in simple terms, is a piece of code that runs on the blockchain. And when we say a piece of code, it's basically a bunch of if-else statements, right? And what this means is that it basically just helps set some sort of like preconditions. And once those conditions are met, it is executed. So what this means is that you write a smart contract, a multi-sig smart contract, and you tell it that, oh, until certain users have validated my token transfer transaction, that is when you should send out the token. And so your multi-sig might have 3 validators, right, and 2 confirmation policies, right? That would mean that 2 persons have to sign my transaction before the transaction is executed. This is a simple multi-sig analogy, right? And so once this is encoded in smart contract, it basically means that 2 persons from like your confirmation policy or owner policy needs to sign the transaction before the money is being sent out. This is basically just encoding business logic on chain. And what helps us do that is smart contract. Now, smart contract, like I said, is a piece of code that runs on the blockchain. Now, what is the programming language for writing smart contract? For the most part, for EVM compatible blockchains like Ethereum and also Kaia, right? Solidity is the popularly used smart contract language, right? It is used on quite a number of blockchain, Ethereum, Kaia, Optimism, Polygon, and whatnot, and so forth, right? And so we have other programming language that is used for smart contract. We have Viper, we have Yule, we have Cairo, which is used on the Stacknet ecosystem. We have Rust, which is used on Solana, Polkadot, and Cosmos. We have Move, which is used on Aptos and Sui, right? So these are quite a number of like various smart contract programming languages, right? But for the most part, for the purpose of this bootcamp, because Kaia is EVM compatible, right? We're going to be focusing on writing Solidity, right? So the next on the list is to understand Kaia virtual machines, right? I mentioned EVM, right? EVM is basically Ethereum virtual machine. Now, KVM also, Kaia as a blockchain also has its own virtual machine, and it is called KVM, right? And so KVM is basically a runtime environment where smart contract lives and also they are being executed, right? Basically, just like how you have Android OS for mobile apps, or right, we also have virtual machines for like smart contracts, right? Pretty much it. So it's important to note quite a number of few things that smart contracts are written in Solidity, right? But then Solidity is like the high-level language, and then it needs to be compiled into bytecode such that the KVM can understand and also execute based on the various opcodes available in the bytecode, right? One thing to also note is that KVM is Ethereum, is compatible with Ethereum virtual machine. And so what that means is that all of the development tools, all of the opcodes, all of the frameworks and libraries available on Ethereum can be used on Kaia. So take, for instance, in this bootcamp, we'll be looking at how to use Hardart, Foundry, and whatnot, how to use Vim, how to use Kaia, or how to use like other type of Ethereum libraries, right? All of these Ethereum libraries or like frameworks or development tools are also compatible with Kaia, because Kaia is what EVM compatible, right? I hope that makes sense. So very quickly, let's just talk about the last two, and I think we'll be done for today, right? Yeah, we have wallets, right? So what are wallets? For the most part, right, I think a lot of us will or must have seen wallets or must have heard of wallets, Kaia wallets or MetaMask, right? And so what are wallets in this case, and what do they actually do on the blockchain? You know, we talked about transactions, right? And I said transaction is like how the blockchain states are mutated, but the transactions have to actually originate from somewhere. And so for the most part, wallets are designed to store digital assets and also initiate transaction on the blockchain, right? They basically hold your assets. Take, for instance, your Kaia tokens, your Ethereum tokens, or your Bitcoin, and whatsoever type of tokens, right? And so they help you to like store digital assets and also sort of like interact with the blockchain whether read from smart contracts or write to the smart contract, right? So I think for this guide, we are going to, or for this call, would install Kaia Wallet. How many of us have Kaia Wallet installed anyways? Can I add testnet network manually? Oh, yes, for sure, you can. As a matter of fact, there's a documentation on Kaia Docs that sort of like talks about adding that talks about manually adding what's it called now? That sort of adding, that talks about adding Kaia to your MetaMask, right? So you can either use, after installing your Chrome, you can either just use chain lists to add your network. This is like a quick configuration, or you manually just set your network name, RPC, ID, and whatever, right? Pretty much it. I think you can use this guide to set up that, right? So if you don't have Kaia Wallet, I think you can just head over to kaiawallet.io, right? This link over here, and you're going to be installing it as a Chrome extension. So all you have to do is click on this and ensure that it's added as a Chrome extension, right? Something like this, right? Something like this, right? You should now have your Kaia wallet added to your Chrome extension. Make sure to store your private key or like your seed phrase safely. That's like the first stage, right? Make sure to store your seed phrase safely. Once that is done, you basically you'd be given like a first account, which is like the first account created. Once you have your first account, you want to fund your account. As you can see, this has both mainnets and testnets and local hosts. But because most of like our interactions will be on the testnet. Now, Kaia has two major networks, which is the mainnet and the testnet. So the testnet is the simulation of the mainnet. The mainnet is actually the where the actual stuff happens, right? Where real funds are, right? So while developing or while building, you want to build on testnets so that you can test all of your functionalities, right? And so for that, we have the Kairos testnet. And so to also like pay for gas, right, which is like the computational unit for every like transaction being initiated, right? You have to fund your account first, because initially you would have zero in your account. So you have to fund your account. To do that, you have to head over to faucet.kaia.io to fund your account. All you basically have to do is to copy, all you have to do is to copy your address and paste over here, and then you run faucet, right? Probably just solve all of this captcha, then you should be good to go. All right. Okay, so it says my Kaia faucet request accepted, and if I should check my balance, I should have 50 Kaia tokens right now, right? So now when I refresh, I should have 50 Kaia tokens, right? So that's pretty much how to set up your Kaia wallet, right? Yeah, I think that's like the first part. Now, why are we doing this? Because for the most part, when you are building smart contract and also when you are building front ends, you will need all of this. So you need to familiarize yourself with wallets and also how to interact with them, right? Yeah. So the last on the list for today's class is blockchain use cases, right? I mean, we've been talking about quite a number of stuff. We've talked about the overview, what is blockchain, what are blocks, how that they are chained together. We talked about blockchain core components, cryptography, consensus algorithm, distributed networks, and also we talked about smart contracts and the pros and cons, right? And now the next on the list is to talk about blockchain use cases. Now, what are the various ways at which we can use the blockchain? So I've provided like 6 or 4 industries that blockchain can disrupt. Now, the first on the list is supply chain, right? For the most part, in the traditional world, supply chain is kind of like slow and also is plagued with counterfeit, fraud, or loss of goods, right? We see this a lot, right? Especially when trying to move goods from like production to delivery. There are a lot of like counterfeit products that have been exchanged during this pipeline, right? But with blockchain integrated, right, all of the steps from production to delivery can be recorded on chain, right? This sort of like improve traceability, providing tamper-proof and transparent record of the movement of goods from one place to another, right? What this also means is that it sort of like ensures that goods are authentic, right? Because you can track all of the movement of the goods from delivery or from production to delivery. So that means that if at delivery, you sort of like get a goods, you can easily track them using like their IDs on the blockchain and see, oh, this goods actually originated from the actual source, right? And so this is how blockchain can disrupt, the supply chain industry for improving traceability and also security, right? The next on the list is financial services and banking. I think everyone here will agree with me that traditional banking is sort of like also sort of like slow these days, especially if you are trying to like do cross-border payments, right? There are a lot of like paperwork, right, that you have to do, especially like when you're trying to send money from somebody in another country, especially wire transfers and all of those things, right? Also, the fees that you have to pay is sort of like on the high side, right? You have to pay some sort of fees and whatnot. And now, how blockchain sort of like disrupts this industry is by ensuring faster and efficient transactions. Now, imagine you sending stable coins to somebody in Pakistan, right? At your fingertips, right? You can easily do that, right? Even without sort of like going to the bank to sort of like queue or like wait for 3 days, 3 business working days before the transaction is processed, right? So with blockchain, it sort of like make cross-border payments and transaction faster and also less costly, right? Now you don't have to pay quite a number of like fees when using stable coins, especially when you are trying to like make transactions on Kaia and when you are trying to send USDT on Kaia from one person to another, right? The transaction fee is as low as 0.002 cents, right? Also, we have improved settlement process, right? With blockchain and also cryptocurrency and disrupting the financial services and banking sector. It provides a more secure and efficient way of clearing settlement. Now, also with the blockchain, you can have access to DeFi, lending, and borrowing, quite a number of like other amazing functionalities or quite a number of other amazing use cases that can spring up, which are not like readily available before. You can now have access to like the on-chain and the global economy where you get to be funded from wherever you are in the world, right? That's pretty much it about how blockchain can disrupt the financial services and banking economy. Also, we have real estate, right? I think one of like the prevalent issues in the traditional world is trying to prove ownership or like title that you're the owner of this land, right, and whatnot. And imagine recording title or the ownership of a particular land on the blockchain. And you can easily confirm that, oh, because it uses like addresses that has private key under the hood. You can easily track the owner of a particular, will I say land, because the account initiated the transaction, right, or added the property on the blockchain. So you can easily track digital records of property ownership. And the next possible use case that blockchain can sort of like disrupt the real estate industry is fractional ownership, right? And so this is a way where quite a number of persons can come together to gather funds together and own fractions of a particular real estate, right? And most times, certain real estates are quite expensive. And imagine providing access to a new form of investment class where 50 persons can come together to own a particular real estate, and whatever like returns that is being generated from the real estate, whether from renting out, will also sort of be shared amidst these fractional owners, right? So this is how blockchain can sort of like also disrupt real estate industry, right? We also have education. Now, for the most part, education or like blockchain can disrupt the education industry by enhancing secure, transparent, and portability of educational credentials. Now, we've seen scenarios of students forging certificates or that they graduated from MIT or whatever, and whatnot. Now, imagine if like certificates are recorded on chain and the certificates issuer sort of like have a dashboard where they can sort of like confirm. And because each of the students will have an account or a wallet where the credentials are being sent to. And of course, so you can tie from the certificate issuer to the student that, of course, this student actually graduated from so school or for so bootcamp. Now, take for instance, for this bootcamp, we'll also be issuing a certificate of EVM developer or like a certified EVM developer certificate, right? And so if your future employer sort of ask you, oh, what types of certificate do you have? You can, sort of like use this as part of your learning or part of the credentials that you have. And so that's one way this can sort of like disrupt the educational sector. Now, the last on the list is the public sector. I think I've already mentioned quite a bit about this, where electronic voting systems can be brought on chain. Now, imagine recording a lot of the voting processes, a lot of the voting, on chain, right? Where a particular citizen votes and the vote is recorded on the blockchain. Now, it removes the elements of rigging elections or like manipulating election results, because whatever blockchain transaction or whatever data that is stored on the blockchain cannot be reversed, right? This is what we have seen from like the pros and cons of the blockchain. It's immutable. And the next is land and property management, of course, handling property title and ownership, and also digital identity management. All of the citizens' identity can be recorded on chain and can be used to like tap into other like amazing use cases like DeFi, whatnot, and also like just do stuff on chain, right? I think that would be all for like the use cases. And so far, today, we have been able to look at blockchain introduction, right? We defined blockchain to be a shared and distributed immutable ledger that enables the recording of transactions and also the tracking of assets within a network, right? Pretty much, we talked about the concept of blocks to be the fundamental units of the blockchain and how that it contains various lists of transactions and also the cryptographic hash of the previous block, right? Then we talked about the core components of the blockchain, how we mentioned cryptography, we mentioned consensus algorithm, we mentioned distributed network, smart contracts, and also the virtual environment for running and for integrating smart contracts. Then we talked about wallets. In this case, we saw how to download your Kaia wallet, right? I think most of us already have Kaia wallets, and I kind of like showed a way to import Kaia network into your MetaMask if that's what you're using, and also how to fund your accounts, especially on the test network, Kaia Kairos testnet, right? And also we talked about blockchain use cases, And I think that'll be all for today. Yeah. And so for today, we also have like an assignment or like a task, right? I think I'll just go over the task, right, Sean?
Sorry, what?
I said, I think I'll just go over the task, right? Or do we take questions and answers?
I think a lot of the questions have already been answered in chat.
Oh, okay.
Yeah, I think due to we are almost coming up on 2 hours here, we should go straight into the task. So I think in the future, what we can do, Ayo, we should take note of this, is we should have a QR code to the slides. I think that'd be quite useful. Yeah, on the actual
Okay.
slides themselves. Yeah. So do you want to send, do you want me to send the task submission form in the chat, or do you want to just, you know?
Yeah, I think I'll just go over it and you can share afterwards.
Okay, cool. Go ahead. Yeah.
All right, awesome. So the task for today is to download and install Kaia Wallet. And so if you already have Kaia Wallet, I think you are good to go. The next is to fund your account via the faucet, which is faucet.kaia.io, which directs you or redirects you to this URL, right? And once that is done, you want to create another account, right? Because you have a first account, then you want to create another account on Kaia Wallet and send one test Kaia to this account from your first account, right? That's the third step. And then you want to send the transaction hash of the transfer transaction by copying the transaction hash on Kaia Scan, right? And so this is like the assignments. Now, the objective of this is to basically show you how to uh, first have a wallet and also interact with the blockchain by sending a transaction. Because we mentioned that, a block contains various lists of transactions, right? And then you want to copy the hash of that transaction. And then what you're doing next is trying to now see some of the block details or the block elements. Now, the first thing you want to do is to submit the transaction hash. Then next is to submit the previous block hash in the block which your transaction was included. Then submit the block size of the block your transaction was included, and also submit the transaction count of the block your transaction was included. So this is you basically trying to play around the blockchain, right? And seeing these things firsthand yourself on Kaia Scan, which is a blockchain explorer for the Kaia chain, right? So that's pretty much the assignment, and the deadline will be on Friday, 6th of June, right? So I'm going to be closing this submission form on Friday, 6th of June. All right, so I think that will be all, right? Thank you very much, guys. Let me check if we have any type of question.
Yeah, I just sent the Google form in the chat as well for everyone who is here. Can go ahead. It's a pretty easy one to do. I think just install Kaia Wallet and create your first account, a wallet.
Right.
Right, it should be quite simple to do if you all have made it this far. Right, if you're still unclear, I think there are many tutorials online. But yes, of course, yes, we'll send it to the description. We'll send it right now, actually. Yeah, so it should be quite simple to do, as I mentioned before. To those, yes, yeah, where's my thing? Yep, here it is. I have way too many chat groups tabs open, but it's okay. Shoot. This is all the slides here. Oh shoot. Uh-oh. Oh well, you guys can get a thing. Here's slides. Here it is. Okay, I will go ahead and send us the slides. If there are any further questions, go ahead and ask it in the Discord. And yeah, if other than that, yeah. All right. Thank you all for coming to this live session. And as usual, this will be recorded. I will try to upload this as soon as possible. Yes, we will try to. Yes, I will try to resolve the ban on Discord. For those that are banned, please feel free to email back the email that is sent. I think you guys can find the email that was sent to you guys. Just go ahead and reply to the email saying, "Hey, my account is banned. You know, help me figure it out." Yeah. So yeah, Ayo, any parting words to our fellow bootcamp participants here? Are you on mute?
Yeah, I mean, just like word from yesterday, that greatness isn't born, it's grown. This is like the first step, right? And how that um, the Build on Kaia Bootcamp is more like the incubator to grow that Kaia builder soul. And so, yeah, we are excited to do this with you guys, to take you from 0 to 1. And don't stop building and don't stop learning. If you do have any questions, please do send them on Discord. That's like your playground. Ask questions, don't be shy. You have quite a number of like resources or helpful hands to sort of take you from 0 to 1. So please do maximize this opportunity, right? I think that'll be all. And also see you guys on Friday.
Yes, our next lesson is on Friday. I think that will be the session that is actually live streamed out. Can you remember me what the lesson was on again? Ayo?
Kaya ecosystem, right? Just doing a deep dive into Kaya itself, the
Yes, we will have a very
technology.
special guest, Neo, who's our ecosystem lead, or I'm not sure what his role is now.
Head,
But yeah, he will be guest
head of.
speaking for us, right, Ayo?
Mhm.
Yeah.
Yes.
So yeah, I really am glad that everyone came when they did, as usual. I know currently we have about 20 plus of you guys here. Yes, thank you. I think we can call Professor Ayo, maybe. I don't know. But yeah, thank you all for attending the session live. Well, we are still looking for any feedback. So any feedback you have, please feel free to type it in Bootcamp General. Was it too draggy? How did you find it? In terms of, would you rather have prefer just a regular recording of this? Well, I said we're looking for feedback. This is our very first time doing live sessions, actually, like this kind of Zoom session. So any feedback is instrumental in for future bootcamp participants. Yes. So yeah, if there's nothing else, thank you all for attending. Yes, thank you all, and thank you all in the chat. Yeah, and we'll see you all on Friday at the same time. I think now it's like 2 o'clock West African time, 9 p.m. Singapore. Yeah, so we'll see you guys on Friday. Hopefully everyone's here on Friday. I'm hoping there's probably a bit more for you guys on Friday because it's a bit more interesting topic. But yeah, please on the form submission of assignment, no track of record of mail activation student. Oh yeah, Ayo, we may need to edit the form to have their emails.
Okay. Okay.
Yeah, just to make sure that you've done the task. Yeah. Okay, cool. Yeah, so if there's nothing else, I'll end the session here. Thank you all for attending. See you guys on Friday. Okay, cool. Okay, bye guys.